I am the leprechaun. Today in the Physics Funhouse, we are investigating some of the properties of light. Come with me if you dare. Today in the Physics Funhouse, we're investigating diffraction, specifically the question of whether or not light undergoes diffraction when it passes around a barrier or through an aperture. And so if you go and Google image search diffraction of waterways, you can find lots of pictures like this that show the bending of waterways as they pass around a barrier, like in this picture. We should be able to see kind of circular patterns in the waves, or through an opening or aperture, like in this picture right here. And if possible, I'll link a video of somebody demonstrating the diffraction of waterways. Our question today is, does light do the same thing? And this was a question that was first asked by a fellow named Thomas Young in the early 1800s. 1803 was when he first proposed this to the Royal Society in England. He proposed an experiment in which you took monochromatic, or one color, one singular color, light through two openings in a card, and basically you'd make those with a razor blade and a piece of card, real narrow slits. You need two of them for this experiment to see if the light diffracted through those openings and then interfered to give an interference pattern. And what he was proposing was a test of whether or not light moved as a particle or as a wave. And so up until this point, everybody basically accepted Isaac Newton, to you and I, theory that light was a particle. He explained everything in his book about optics and light, assuming that light moved as a particle. So the experiment that Thomas Young proposed in 1803, today we often refer to as the double slit experiment, because he took a piece of card and he cut two slits in that piece of card with a razor blade, and then shined a single color, I'm going to draw a green light for my example, of light onto that card, and on the other side of the card he put some sort of screen. We're just going to use a giant whiteboard today as our screen. And if light is acting as a particle, moving as a particle, as it reaches the slits in the card, only light should pass through the slits that is actually like an incident on the slits. Everything else would be reflected. And then like the light itself shouldn't change as it goes through the slits, and we would simply see, a pile of light here and a pile of light there. So there would be two bright spots on the screen immediately adjacent from those slits when you did that. So that would be what the particle model would predict. The wave model of light, if light is moving as a wave, as those waves of light reached the card and went through the slits, they would diffract as they moved through those slits. So they would look something like this as they came through, and that would happen at both of them. Look something like this. And we hopefully remember that when two waves are occupying the same space at the same time, they are going to interfere with each other. And at points where the crests line up with other crests, we're going to get constructive interference. And then if that point happens to lie on the screen and we're observing it, we will see a bright spot. And then at points where there is a crest lined up with a trough, we'll get destructive interference and there'll be no light. And so what the wave model of light suggests and predicts in this experiment is that we should have one bright spot in the center, which would be adjacent to a dark spot on either side, so constructive interference, destructive interference, and then another bright spot above that, and below that, and then another dark spot above and below, and so on and so forth. Something sort of like this. And so what the wave model suggests is that when we pass monochromatic single color light through the two slits in a card, we should see stripes of light over here on the screen. Bright, dark, bright, dark, bright, dark stripes as we look at it on the screen. In 1803 and 1804, when we actually published the results, getting green light was not a simple thing. It's not like you can just go print out a piece of acetate and cover up a light bulb to get green light. And so these guys had to figure out things like prisms to separate sunlight into colors and then block out the other colors. It wasn't a simple thing. It's going to be simple for us because I can get monochromatic green light using a laser. A laser will produce a single color of light. So let's go back in the lab. Let's play with lasers today. So what I have back here is a green laser, and you can see the point of the laser up there on the whiteboard. And kind of get out my hand there. So green laser, I'm using a green laser because it's a little bit brighter, I think, than the red laser, so I'm hoping it shows up better on the video here. This is a plastic slide that's on kind of this little rotating axle thing. And what it's got in there, you can see, is real narrow little slits. And so if you look at the bottom, the slits come in pairs, and that's what we're going to be looking at here first. And so I think this one kind of shows up best so far here on the camera. They're two really narrow little slits that are relatively close together. That's two slits as well. They're just kind of close together, too close together to really see. Here you can kind of tell that there are two slits cut in the plastic right there. And what we're going to do is we're going to shine our laser light through, probably start with these two slits right here. And what we're going to look for is, does the light, after it passes through the slits, create two dots of light on the whiteboard, which would happen if light was a particle. Light could only go through those two slits and then would keep moving in a straight line at a constant velocity until it hit the whiteboard. And so if light's a particle, as it passes through those two slits, we should just see two bright dots on the whiteboard. If light is a wave, however, then we should see the light diffracting as it goes through those two narrow slits and then interfering with itself on the whiteboard. And so we should see like stripes of light, like a bunch of bright spots, bright, dark, bright, dark, bright, dark. So let's get this thing lined up on this track. And so I got this nifty little track that kind of holds all these things in place, which is going to be real handy because I'm doing this by myself. Let's fire the laser.
Begin laser ignition sequence.
Begin laser ignition!
They don't make cool sounds like they used to do. So you can see that the laser dot is incident now on the double slit. And if we now point it over here at the whiteboard, hopefully what we can see is there's a bright spot in the middle, followed by a dark spot, and then another bright spot. And basically we have stripes of light instead of two dots, indicating that light is diffracting and interfering. Therefore, this is evidence that light is a wave. So with the lights off in the room, you can clearly see there's a bright spot in the center, a maximum, and then a dark spot, and then another bright spot, dark spot, bright spot, so on and so forth. If I move the plastic slide to a different set of double slits, now you can tell that the bright spots and dark spots are a little bit more spaced out than they were before. Try a different one here. So you can see the really bright stripe in the middle, and then a dark stripe, and then another bright spot, dark, bright, so on and so forth. There's another set of double slits. And then there's another one. That one produces really nice tight dots. It may not be as easy to see that there's a dot and then a dark spot, a dot and then a dark spot. So we can get zoomed in a little bit more. But there we can see that instead of two bright spots, we have stripes of light, dark spot, bright spot, dark spot, bright spot, dark spot, bright spot, going up and down the whiteboard. So again, this is strong evidence that light is a wave and not a particle. It diffracts and it interferes. So back there in the laboratory, we saw stripes of light when we passed our green laser light onto that little piece of plastic with the two slits cut in it. We saw stripes over here indicating that Mr. Young's prediction that light could act as a wave was correct. And since the wave model of light predicted stripes, we observed stripes. Our conclusion today is that light is moving through those two slits onto the screen as a wave, not as a particle, which goes directly against what Mr. Newton said about 150 years earlier regarding the movement of light. He assumed light was a particle, and he was able to successfully explain a lot of things with that assumption. The cool thing about the Young experiment, and this is something I'm not really able to do in my lab yet, I'm going to keep trying. So people were challenging the results of this experiment, and they said, well, if you took a coin or a marble or a sphere of some sort, and you passed monochromatic light around it, you should get a similar effect where all the light surrounding it should be bent towards the middle by diffraction, and at the center of the shadow you should see a bright spot. And it's really difficult to actually observe, but they set the experiment up very carefully, did a really good job of making sure that they had monochromatic light and nothing else interfering. Looked at the center of the shadow, and lo and behold, there was the bright spot. And so the Young double slit experiment withstood all challenges to its legitimacy. And so after 1800, we start to move forward with the wave model of light as being the accepted model for light. As it turns out, in the 1900s, starting with some guys like Einstein and his ilk, we actually kind of revisit that question. But we'll get to that then. For now, let's go back in the lab and let's use the double slit experiment to see if we can figure out the wavelength, because if light's a wave, it should have a wavelength, of laser light, and see if we can use it to measure really small things, like how far apart these slits actually are. So let's return to the lab. Let's play with lasers a little bit more. The interference pattern that was created by the double slits was obvious. We could see it on the whiteboard, but it's not very easy to measure the distance between the maxima and minima for something like the just two narrow slits cut in a piece of plastic. The distance between them is very small compared to like the edge and fuzziness and blurriness of those dots. So we can do the same kind of experiment that Mr. Young did. He used the two slits cut in a piece of card. If we cut many slits into a piece of card, and that's what this is. This is called a diffraction grating. Essentially what it is a piece of plastic that is opaque, but we cut a bunch of slits into it, just like the little plastic circle that I showed y'all earlier. So again, this is called a diffraction grating, and what we're going to do eventually in this lab today is measure the distance between the really narrow slits in the diffraction grating. So I've got that kind of mounted onto a little mount that'll fit on my track here. I'm going to set it right there. And again, we are going to fire the laser. Fire the laser! And what you'll notice up there on the whiteboard is that now I've got a bunch of really nice, tight, distinct dots that are easily separated by a distance much greater than the width of those individual dots. And then you have up here, this is a reflection, that right here is a reflection of the original laser. And so that's just bouncing back around from the diffraction grating up off the top of the whiteboard. So that's just a reflection of the original laser light. And so these dots down here is the diffraction pattern created by my green laser going through the diffraction grating. So with the lights off, you can a little bit more clearly see the diffraction pattern. So there's our center maximum. And then there's the one adjacent to that, and then there's the one adjacent to that. You do get a lot of scattering of the light off that whiteboard surface. So you see scattering, you kind of see these little bands of light due to the scattering. Those are a little bit less obtrusive in real life than they are here on the video. They don't show up as bad. Oops, I'm blocking the laser with my hand. They don't show up as bad in the classroom as they do on the video. But if we kind of get a little bit closer, you can clearly see a nice tight dot right there, and this is just scattering off the whiteboard surface. So our job here in the lab we're going to do is we're going to measure how far apart these dots are. So what I'm going to do, just kind of demonstrate that here to begin with. Let's back this all up. I'm just going to take this whole apparatus and I'm going to slide it closer to the whiteboard. And it's not so much the distance from the laser to the whiteboard that matters. It's the distance from the diffraction grating to the whiteboard that matters, because the laser light is coherent and it's not going to do anything but travel in a straight line going from here to here. So even if I move the laser forward and then backwards, like the reflections and scattering off the whiteboard change because the intensity of the laser beam is getting brighter as I move it closer. But the distance between the dots doesn't change as I do that. However, if I move the diffraction grating, the distance between the dots does change. And so let's move it by a lot. Let's scooch this whole thing forward. So you notice that as the diffraction grating gets closer to the whiteboard, those dots, the maximum minimum, get closer together. So what we're going to do is strap a meter stick to that whiteboard, measure the distance between those dots versus the distance from the diffraction grating to the whiteboard. And from that, we should be able to, knowing the wavelength of the laser, calculate the distance between the little tiny slits in the diffraction grating. So let's get that experiment set up. Okay, so here's my experimental setup. I've got my green laser, and there is the diffraction grating. And those are not going to move relative to each other, and that distance doesn't really matter. And I've kind of got this thing scooched about as far back as the power cord will let me reach here in my lab table. And I've got my lab table marked off in 1/4 meter increments. And so I'm just going to move these to these different spaces along the lab table. And we're going to call that value L. And so L I've already kind of predetermined. I'm just going to move it to different positions. And then over here, we've got a meter stick set up so that we can measure the distance between two successive maxima. It doesn't really matter which ones, so I'm just going to try to shoot for the center one here relative to that one over there. And my meter stick is nice and leveled with those magnets underneath it. This is actually kind of a great way to make a easy laser level for hanging up pictures in your home, because the light will find its own level. So let's back it up over here. I'm going to turn the lights off as I do this so that it's easier to see those dots up there on the meter stick. Okay, so taking my first measurement at 2.25 meters, that's the value of L. Over here on the meter stick, the center dot is at 52.3 centimeters. And the next dot over here is at 28.7 centimeters. And so this distance Y is 23.6 centimeters. So converting that to meters is 0.0236. And then we're going to scooch our whole thing forwards until the front edge of my diffraction grating is at 2 meters. Carefully looking at it from above. Okay, so hopefully you kind of notice that those dots got closer together up there on the whiteboard. Okay, so let's go and organize and graph that data and see if we can figure out how that tells us the distance between the slits on our diffraction grating. Okay, so there is my data set all kind of cleaned up and kind of rewritten without the mistakes and scratch outs and stuff. There's one other important piece of information that we're going to need before we can figure out the spacing between those slits, and that's the wavelength of the laser light. And so if we kind of come down here, we get in real close, maybe move the cord out of the way. So here on the laser, you can see that the wavelength is given. It's 532 nanometers. So nanometers is what we're looking for the wavelength. So let's go ahead and add that to our data set here.
lambda, and I'm going to make sure I write down that this is the green laser, equals 532 nanometers. Yeah, double checking. Okay, so now we have a complete data set that we can graph and figure out the distance between the slits cut in our diffraction grating. So let's head over to a computer and let's graph this using a computer, because otherwise these numbers are going to get kind of yucky.
Okay, so in order to understand what all happened back there in the laboratory, we need to kind of draw some triangles and do a little bit of geometry together. And we're going to make a few simplifying approximations along the way. So when I tell you something is a right triangle and you go, wait a minute, that's not really a right triangle, it's okay. It's approximately a right triangle. So here's our picture. Over here in the pink, this is our diffraction grating. I've just gone ahead and drawn it as two slits for simplicity's sake. So this is like the very first demo I showed you, where it's two slits separated by a distance of d. And d is what we're looking for in this first experiment. The distance from the slits to the whiteboard, or screen, speaking more generally, is distance L. That's the yellow dashed line. And then the distance between two bright spots, or two maxima, is distance y. And so back there in the lab, we measured distance L and we measured distance y. We varied L to get different y's. The green lines represent the light after it's been diffracted through the slits. And so the solid lines represent diffraction that would cause constructive interference at this spot, giving us a maximum. That's the center bright spot. And then the dashed green lines represent another set of diffracted waves that also interfere constructively to give me another maximum bright spot due to constructive interference. So what we need to remember is that the only way we're going to get constructive interference is if the waves overlap crest to crest or trough to trough. So the two solid lines, this should be kind of easy to see, that those lines are basically the same length. And so if the lines have the same length, whatever orientation the waves are here, let's just say they're crests, would have to be the same when we get to this point right here. Crests also lined up with each other. If we go up one maximum, hopefully you can tell that this dashed line is shorter than this dashed line. This dashed line is just a tiny bit longer. How much longer? It has to be exactly one wavelength longer. And so if we were to drop a perpendicular bisector from the opening of this slit perpendicular to this dashed green line, that would approximately give us a right triangle, approximately an isosceles right triangle, hence the approximation thing, where this dashed line and this dashed line are equal to each other. And so what you get then is a triangle formed by the remainder of this, that, and that, which is also approximately a right triangle. This side of our right triangle, the leftover dashy bit of this green line, is exactly one wavelength. So if the leftover part of this dashed line is equal in length to this dashed line, then the remainder of the first dashed line has to be one wavelength. Otherwise, it would not have interfered constructively at this point to give us a bright spot. If it was 2 lambda, that would be the next bright spot going up. And so this little triangle formed right here lets us relate the wavelength of the light to all these things that we measured. And so if we choose an angle up here in our triangle, that right there, I've got a right triangle that's formed by an angle, D, and then lambda, or some multiple of lambda. So if this was the second one, it'd be 2 lambda, 3 lambda, 4 lambda, etc. So in general, what we say is that the sine of that angle, which would just be opposite m lambda. So m is some integer. In this case, it's going to be 1, but it could be 2, 3, 4. If m was some half number of wavelengths, so if m was 1/2, 1 1/2, 2 1/2, etc., that would give you destructive interference. That would be the dark spots.
on the screen. And then the hypotenuse of that triangle would be D. And so we can write that that triangle highlighted in yellow, sine theta is m lambda over D. We can also make the claim that the triangle formed by L, the line that goes straight from the middle of the slits to the screen, to the maximum, and then back, is a similar triangle to the one that we highlighted in yellow. And so that means that this angle here has to be equal to that angle there. And so I have another right triangle. It's a similar triangle to this one. The dimensions of this triangle I measured are L and Y. So L is the adjacent side, Y is the opposite side. So for that triangle, I can write something like tangent of theta equals opposite over adjacent, Y over L. And so I can relate the actual measured dimensions, the yellow equation, with the things I really can't see, which are the distance between the slits and the wavelength of the light, with similar triangles like this. There's one more fun part to this. That can be good enough, and you can solve for the angle between the two things, between Y and L, and then come over here and then from that angle calculate the distance in this case. That's kind of cumbersome and tedious. And so what we're going to do in most light situations is we are going to use what's referred to as the small angle approximation. And essentially what the small angle approximation is that if you have something with a small angle, let's draw a sort of to-scale example of what that looks like. So here is one side of a triangle. And let's scooch this up to like a small angle, like 7 degrees, for instance. Let's draw a line like that. So what the small angle approximation essentially says is that since the angle is very, very small, the adjacent side and the hypotenuse are approximately equal to each other. Like this side is not much shorter than this side. And so what we can then do is we can make the claim that the sine of theta is approximately equal to the tangent of theta. So this theta here with my little ruler, assuming that thing is giving me accurate angles, is about 7 degrees, which is kind of the upper limit of where the small angle approximation would be valid. So if we can apply the small angle approximation to this situation and claim that the sine of theta is equal to the tangent of theta, then what that means is that we can claim m lambda over d is equal to y over L. And that's going to be our starting point for figuring out what to graph in our lab today. So I'm going to slide this over. M lambda over d equals y over L. And that's the relationship between all those variables. We know lambda. We read that off the laser. We measured y's and we measured l's. M we're going to set equal to 1. And I chose to set m equal to 1 moments ago when I measured from one dot to the next dot. And so m is 1 when you go from one to the next. And then we're going to attempt to figure out what d is. And so in order to graph this thing and get d to be my slope or y-intercept, I want to try to make this equation look like y equals mx plus b. And so the first thing I need to do in order to do that is to get my variables on opposite sides of the equation. So these are the two variables that I measured. Lambda was held constant, and d should be constant as well because it's fixed. The distance between the slits and the piece of plastic weren't changing. And so what I might do is just multiply both sides by L. I'm going to go ahead and drop the lambda, or excuse me, the m from now on. And so if I did that, multiply both sides by L, I would get something like L times lambda over d, kind of like that. And so if I have one variable isolated on one side of my equation, well, that's just going to be my y variable, or vertical axis, whatever you want to say. The variable on the other side would just be my x-axis, or horizontal. And the thing that's being multiplied by the horizontal variable, multiplied by x, would simply be the slope. Y equals m times x. And so if I graphed y on the x-axis, if I graphed y on the vertical axis, and I graphed L on the horizontal axis, the slope should be lambda over d. If I wanted to, I could go ahead and combine lambda and L, because lambda is a constant, meaning L times lambda would just be a scaled up variable, in which case the slope would be 1 over d. There's a couple of different routes that I could go from there. If I wanted the slope to just be d, then I would need to get d over here on the other side, so that'd be in the numerator, and I could play games like that. And so as long as we can write the equation in y equals mx plus b format, and then find the y variable isolated by itself on one side, the x variable times whatever on the other side, that whatever is going to be the slope of the line, and then I can use that slope to figure out what I want to figure out. In this case, it is d. So for simplicity's sake, I'm just going to graph y versus L. So kind of sketching that here. I'm going to put y on the x-axis, I'm going to put I'll put y on the y-axis and L on the x-axis. Hopefully that gives us a straight line. And then once I have that straight line, I can find its slope, which is going to be equal to lambda over d. And then once I have the slope, that's just going to be a number. I can solve for d, multiply both sides by d, divide by slope. So in this case, I'm going to find d by doing lambda divided by the slope. Okay, so I've graphed my data in Excel, and over here I've got my y values, the distance between the maximum. Over here I've got my L values, the distance from the diffraction grating to the screen. And you'll notice I've got a pretty nifty straight little line here. I'm actually kind of pleased with myself here, considering I did this all by myself in my lab like late at night. Up here I got the equation of my best fit line, and the plus 0.0003 tells me I've got a y-intercept of practically 0. The slope right here, the number in front of the x, is 0.105. And so let's go ahead over here and write 0.105 down for our slope. And so just like always when we use a spreadsheet like Excel to graph, we do need to stop and think about what the unit should be. The unit for y is in meters. The unit for L is also in meters. And so a meter over a meter is nothing. There's no unit. It's unity. And so the slope is just 0.105. That's kind of important then that I recognize I'm not going to get this right if I've got y and L in different units. I got those in different units. I need to adjust them and make sure they're in the same unit. And it actually doesn't matter which unit I use. I could have used centimeters, and I would have gotten the same slope as long as they're both in centimeters. Okay, so now that I know what the slope is, I know that I can find the separation between the slits by dividing that slope by, dividing the wavelength by that slope. So I can do d equals, the wavelength of our laser light was 532 nanometers. Divide that by a slope of 0.0105. And just like before, it's important to recognize the unit I'm going to get here. My answer is going to be in nanometers, because that's what my wavelength is expressed in. 5,067 nanometers. And so those little slits are kind of close together, aren't they? So 5,000 nanometers, not terribly large there. So what we're going to do next is take the same diffraction grating and shine a red laser through those and repeat the experiment. Do a bunch of different Y values versus a bunch of different L values, and then calculate from that the wavelength of a laser. So that's going to be your job to figure out. How can we use this relationship with a known D, now that we found that using the green laser, to calculate the wavelength of a red laser? And then we'll compare that to the actual wavelength stamped on the red laser and see how close we get. We'll do that in a separate video. Okay guys, there's one other thing that I want to show you that's actually kind of interesting. I've got my laser, red laser still, got my diffraction grating, and this time I've got this black background. And I want to show you something interesting about the scattering. So I want you to look like right in this area right here.